Okay, can you see my screen?
Yes, sir.
Okay. So last day we started talking about graph, and it has lots of applications in different domains. We'll continue our discussion on different kinds of graph and try to finish graph by today. And then we'll briefly talk about tree. Tree is also a graph. So we'll continue talking about tree, because although tree has large implication, but will not go into depth, because you will learn tree eventually when you will study data structure or algorithm courses. So I'll not spend too much time on that. And then we'll move on to discussing about set, relation, function, those things. And that's all about your final exam, because we don't have enough time. So that's our goal. And so feel free to interrupt me whenever you have any questions. And it's better to unmute yourself and just interrupt me. And feel free to send me an email if you have any, if you want to meet me to discuss something, or if you have any queries or doubts, we'll go through that. And in the meantime, I might also upload a couple of by tomorrow. My plan is to we have covered so far till today. So a small assignment, it would not take too much time. So my plan is to release by tomorrow, and you will have around 1 week to submit that assignment. That's the overall basic plan. And yeah, let's continue our discussion. And last day we end with the topic that we discussed was bipartite graph. One very interesting graph. And let's briefly talk about this bipartite graph, and then we'll continue our discussion to explore different new kinds of graph. And bipartite graph would be very easy to demonstrate. Suppose this is Dr. X, this is Dr. Y, this is Dr. maybe Z. These are set of teachers or faculty members at AUM. So just think these are set of faculty members, and this is courses offered by each faculty members, or courses taught by each faculty member. Suppose Dr. S teaching data structure. So this may be data structure, and Dr. X, this is algorithm. This is math, discrete math. This is maybe networking, and this is maybe software engineering, like that. So what teaches, just assume only district teaches networking as well as software engineering. So this is an example of bipartite graph. Just note down that no teacher teaches another teacher, right? So X will not teach Y, Y will not teach Z. Similarly, one course will not teach another course, like data structure will not teach algorithm. Algorithm will not teach discrete math. That's why there is no age in between two courses or in between two faculty members. So this is one kind of bipartite graph where each age represent that one end would be at the faculty point, means one end would be that faculty name, and another end would be the course name. And it has large application on different real life problems. And what one thing you have to believe me, right now, because I cannot go into that details right now. But whenever it has large implication or application, when you will study networking, when you will study algorithm, when you will study data structure, then you will, even the database, you will come to know slowly the implication or the application of those information. So for now, just believe me that they have large implication. So just try to understand the big, try to learn the big picture. So this is bipartite graph, example of a bipartite graph. Again, in bipartite graph, we can all courses and the faculty name, you may consider all is denoted with this dot, is represented is represent as vertex or vertices of that graph, and this is edge of the graph. So and this is one vertex. This is another vertex of that graph. So bipartite graph is such a graph where you can divide the vertices into two sets. This is one set. Set is nothing but a collection. So this is a set of faculty members, and this is set of courses. So you can divide vertices into two sets such that for each edge, one point lies to the set of faculty, another endpoint will lies to set of courses. So this is bipartite graph. So let's, related to this, let me ask you one thing. You have to say true or false. I'm writing one statement. You need to find out whether it's a true statement or false statement. That is, a simple graph is bipartite if and only if it is possible to assign one color Okay, so it is saying that a simple graph is bipartite if and only if it is possible to assign one of two different colors. You have two different colors. You will assign one color. You can assign only two colors to every vertices such that no two adjacent vertices. Adjacent vertices means neighbor vertices. No two adjacent vertices are assigned the same color. So let's take this example. Here, let's assign what are the, this is one vertex. Adjacent vertex means it which vertex is directly connected to this vertex through an edge. So adjacent of this vertex would be these two vertices because they are directly connected with an edge. So if we assign red to this node, we cannot assign red here. So let's assign here green. And we can also assign red here. Also, we can assign red. Now see, these three vertices are not adjacent because there is no edge which connects those vertices. On the other hand, we can color, okay, these vertices as green because they are not adjacent, because there is no edge in between those vertices. So we can color all those vertices in this set as green, and in this part here we can assign only red color, one color to every vertices. So the graph is that statement is saying that a simple graph is bipartite if and only if it is possible to assign one or two different colors. Here we have used two colors, red and green, to each vertex of the graph, so that no two vertices, adjacent vertices, neighbor vertices are assigned the same color. So that means the statement is true. So any bipartite graph, you can assign two colors, only you can use two colors to color those graphs such that no two adjacent vertices share the same color. This is also called color theorem. We'll come to that point maybe end of the today's lecture. So that's also important point, color theorem. So I hope it is understood. And yeah, so any bipartite graph, you can assign only two colors so that no two adjacent vertices share the same color. So we can take small example, like this is one graph. First question is it bipartite? And next question would be, what is the minimum color required to color the graph such that no two adjacent vertices are assigned the same color. So first, is it a bipartite graph? Bipartite means here there are four vertices A, B, C, D. Now we can divide this A, B, C, D into two sets such that two members of a single set doesn't have any in-between edges. Like here, we can convert this graph like this way. Here, A and C, there is no edge in between A and C, and there is no edge in between B and D. So we can keep A and C in one set and B and D in another set. So this is A, C, B, D. Now see, there is an edge between A and B. So put that edge AB, another edge from A to D. So put that edge A to D, another edge from C to B. Put that edge C to D. So it holds the bipartite property that C, there is no edge in between A and C, there is no edge in between B and D. So the total vertices was A, B, C, D. We can divide A, B, C, D into two sets. One is AC, another one is B, D, such that there is no edge in between A and C, there is no edge in between B and D. So this graph is a bipartite graph. So the answer is yes, it is a bipartite graph. Now the second part of the question is, how many minimum number of color that is required? So since it is bipartite graph, obviously we can use only two colors. What are the color? You can choose any colors. Okay, where is? Yes. So let's assume we color it as red. If we color it as red, you cannot color B and D as red because B and D are directly connected to A. That means B and D are adjacent to A. So we need to color, we need to use different color for B and D. But we can use the same red color for C because there is no edge between A and C. So let's use different color for B. So I use green for B, and I can also use the same green color for D because there is no edge between B and D. So the minimum color that is required is also 2. And obviously it is a bipartite graph, so the minimum number of color that is that you need to assign is 2. And again, we'll talk about graph coloring theorem at the end of this course, at the end of this class. And let me share you one important point here. It would be very exciting to know that throughout this graph algorithm, graph theory, you are going to be introduced with different problem that is open problem, that are called open problem. Open problem means no one has efficient solution for those problem till today. And if you can give an efficient solution, efficient means mostly time efficient. If you can give any time efficient solution for a particular problem, then you will get prize, similar kind of Nobel Prize. So these are all open problem. No one does have any answer, efficient answer. There is an answer, but that is not efficient. That is exponential time it takes. But we are looking for much faster algorithm. And you will briefly introduced with those problems here. At the same time, when you will study algorithm in your future semester, you will be introduced with such hard problem. Those problems are called hard problem because no one has any efficient solution for those problems. So you will be it would be very exciting to discuss those hard problems. Some of them will be discussed today in today's lecture. Okay, so another one, we can do another practice. That is, this is one graph, A, B, G, F, okay. The question would be, is it bipartite? In the beginning, it might look like a slightly complicated graph, but apply the same color theorem. If it is bipartite, then the number of minimum color required would be 2. So try to do that. And one restriction is no two adjacent node should share the same color. What is adjacent node? Adjacent node is nodes which are directly connected with an edge. Now you can assign one color red to vertex A. A and B are not directly connected to each other. So A and B are not adjacent. So we can also apply the same color. Again, don't be confused with whether A and B would be adjacent or not, because they are sitting close to each other. That doesn't mean they are adjacent. Adjacent means there should be an edge in between those two vertices. So we can apply the same color to B. Now we can apply the same color to D, because D is not connected to A. D is not neither connected to B. So we can also use the same color to D. Now we cannot use the red color to E because E is connected to B. Also, we cannot use the same color to F because F is connected to A and B both. We cannot use the red color to C. We cannot also use the red color to G. So now let's use green color to C. Okay, we use green color to C. we can also use the same green color to E, because C and E are not adjacent. There is no edge in between C and E. Similarly, we can use the same green color to F, because F is not connected to C or E. Similarly, we can also use the same color to G, because G is also not directly connected to F, E, or C. So see, we have used only two colors to color the graph where no two adjacent vertices share the same color. So the answer would be yes. And another example that we can do would be, it is a very small graph, but it might look slightly confusing. Okay, so this is another graph. Now, how many colors do you need for this graph? So just try, okay, just color it as red. So you cannot use the same color to other vertices. And if you color it as green, no problem, you can color it green. You can also color it green because they are not adjacent. You can also color it green, they are not adjacent. Similarly, you can color it green, they are not adjacent. You can also color it green, so they are not adjacent. So only two colors are required to color this graph. And if you draw like a bipartite, then you can convert it like this. This one would be one single, and the rest 2, 3, 4, 1, 2, 3, 4, 5 would be in another set. And this is connected to every other vertices. So these two graphs, this one and this one, actually are same. I hope now bipartite graph is clear to you, and you can expect couple of some questions in your final exam as well as in your assignments too on this point.
I just have one question actually.
Yes, Aditya.
So, is the color theorem used to tell whether a graph is bipartite or not? Is this the use of that?
Yes,
Oh,
you can use this graph, this color theorem. When we'll discuss color theorem, it would be clear much in a better way. But right now, you can think you can apply this color theorem to find out whether graph is bipartite or not. Because bipartite should use only two colors, minimum two colors.
oh,
Okay. Okay, so we are done with the bipartite graph. Now we'll talk about another interesting one, which is briefly talk about the application. If you think of this graph, you can see this is a node which is connected to all other nodes, right? So if you think each node represents a computer, so this middle node, you may think is server, and all other computers are connected to that server. Now think this server is not working. If server is not working, all other nodes will be lapsed. They cannot work together because every connection is through this server. So this is one application to know the bipartite approaches. So you will eventually come to know many applications, such applications, real life applications of this graph theory. Okay, next we'll talk about isomorphism of graphs. So let's assume A, B, C, D. This is one graph where it represents that A, B, C, D are friend circle. A is a friend of B and D, B is a friend of A and C, C is a friend of D and B. So it's a B, C, D, a friend circle. And another 4 friends, W, X, Y, Z. So this is another friend circle. So WX, YZ friend circle. And this is A, B, C, D friend circle. Now, isomorphism or isomorphic graph means whether the both graphs are same or not. Iso means same. So iso means same. So you need to find out whether two graphs, they might look different, but whether they are actually the same graph or not. That is isomorphism. So here in these two graphs, you can see if you omit the vertex name A, B, C, D, W, X, Y, Z, just exclude pupil name here, then you will see that both graphs are actually the same graph. It looks like different, but they are actually same graph. Like here, W, X, Y, Z, there are 4 vertices. W is connected to X and Y. Similarly, A is connected to B and D. So if you rotate this graph, just rotate this graph, then you will see the graph is actually same graph. Means if you rotate, then it would look like this one. So if you rotate, so isomorphism means you need to find out whether two graphs are same or different. Iso means same. Now, what is the application? It has large application, believe me. My background is computational biology. In biology, you have, you may heard protein. So protein, you may know hemoglobin. You know, in our blood, we have hemoglobin, which carries oxygen. Hemoglobin is one kind of protein. Whatever you are doing, you can see, you can digest food, everything is because of protein. This is not the same protein which we intake through our food. It is different. It is the unit of the work, whatever we are doing. We are walking, we are thinking, even I am talking, everything because of this protein. Even your eye color is different than mine. Your hair color is different than mine. Everything because of protein. So hemoglobin is one kind of protein, and every protein has some function, unique function, like hemoglobin carries oxygen in our blood. So if you look about hemoglobin, it looks like this. The structure looks like this, round shape, and there is a pocket inside that, which carries actually oxygen. The oxygen is carried through this pocket. So what is the importance? So you can represent a protein like a graph. You can represent a protein like a graph, and each protein contains using 20 amino acid. So each amino acid, you can think a vertex. And so you can represent a protein like a graph. And so suppose this is an unknown protein. You don't know how it works. And there is a protein which is very similar to that protein. It looks identical, and you know it carries oxygen. So your goal would be to find a match. If you can find a match, known match, then you will come to know how this unknown protein will work. So this is one application area where you can find that isomorphic graph. So this is an unknown graph. You will try to find an isomorphic graph which is known to you, so that you can extract information from that known graph. So this is one area where it is applicable. Okay, let's come back to isomorphism. Now the question would be how to find whether two graphs are isomorphic. The answer is no one knows. There is no straight cut rule that, okay, these things happen, so these two graphs are isomorphic. No one can say that. No efficient algorithm exists. But we can give you some conditions. If that condition doesn't hold, then we can say that these two graphs are not isomorphic. So we can have a couple of conditions. If those two graphs doesn't satisfy that, then we can say, okay, they are not isomorphic. That we can say. So let's talk about those conditions. So conditions. One condition would be both graphs should have same number of vertices, which makes sense. Both graphs should have same number of edges. So both graphs should have same number of vertices and same number of edges. And third one is both graphs should have same set of degree sequence. So last day we talked about degree. So let's take one example, then it would be clear. So first, if any of the above conditions do not hold, then the graphs are not isomorphic. If any of these the above conditions, this 1, 2, 3, either one, if either one is not true, then we can say their graphs are not isomorphic, but not the vice versa. Means if all of them are satisfied, that doesn't mean that both graphs are isomorphic. But it is sure if either one is not true, then obviously the graphs are not isomorphic. So let's take one example. Through that, it would be clear. So one graph is like this. This is one graph, and another one is this is another graph. And the question is, are they isomorphic? So we need to find out. So first, what is the number of vertices here? Number of vertices is here 1, 2, 3, 4, 5, 6, 7. Each dot represents a vertex. So number of vertices is 7 here. And what about here? Number of vertices here is 1, 2, 3, 4, 5, 6, 7. Same 7. Okay. So condition 1 was both graphs should have same number of vertices. It's satisfied. Okay. Now, what is the number of edges? Number of edges here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And what is number of edges here? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So condition 2 also holds. Both graphs should have same number of edges. So both are satisfied. Now check, both should have same set of degree sequence. So what is the degree sequence here? This node has degree 1. This node has degree, okay, use different color. So this node has degree 1, 2, 3, 4. Now this node has degree 2. This node has degree 1, 2, 3, 4. This node has degree 2. This node also has degree 2. This node has degree 1. So this is the degree sequence. Degree sequence is nothing but degree of all vertices. And let's take degree sequence here. This node is 1, okay. This node is 4, 1, 2, 3, 4. This node, okay. This node is 2. Oh, I made mistake here. For this node, okay. This node Yeah, 1, 2, 3, 4. Yeah, that's fine. And oh, yeah, for this node, the degree is 1, 2, 3. This node, the degree is 1, 2, 3. For this node, the degree is 2. And for this node, degree is 1. Now see, 3. We have seen that in this graph, there are 2 vertices with degree 3. But here, there is no vertices with degree 3. So that this condition 3 doesn't hold here, because it is saying that both graphs should have same set of degree sequence. But here we have found that the degree sequence are not same for both graphs. Hence, both these graphs are not isomorphic. Okay. Similarly, we can solve another example, which is simpler than this one. This is one graph, A, B, C, D. Another one is P, Q, R, S. The question is, suppose this graph is G and this graph is H. Are G and H isomorphic? So again, you need to check number of vertices. Here is 4, here also 4. Don't think that this is a vertex. The junction point is not a vertex. Okay, don't think it's a vertex. It's not vertex. The edges are, you may draw this in a different way. Just think one is one road on top of another road. So don't think there is a vertex there. And number of number of edges is 4. Here also number of edges is 4, and degree sequence is 2, 2, 2, 2. Here also degree sequence is 2, 2, 2, 2. So according to those 3 conditions, it looks like they are isomorphic. And again, it has a large implication in computational biology, as well as electronic circuits, as well as computer vision, and even molecules in chemistry. So large applications it has. So this is isomorphism. So I'm giving you one homework for practice. So just see that whether these graphs are isomorphic or not. This is one graph. This is another graph. So just see whether they are isomorphic or not. Okay. Next topic, we'll talk about connectivity. And before connectivity, is there any questions or doubts if you have?
I just want to confirm one thing.
Yeah.
So if the above 3 conditions are satisfied, then that doesn't mean that the 2 graphs are isomorphic, right?
Yeah, I'm coming into that point maybe after 20 minutes, because I'll come back to one example where those 3 conditions will be satisfied, but because of some other condition, we will say that those 2 graphs are not isomorphic.
Okay.
Because that's why I said that there is no efficient algorithm exists, no efficient solution exists so far, which will automatically tell you that, okay, this condition holds, so these 2 graphs are isomorphic.
Okay.
Okay. Okay, and next, connectivity. Connectivity is very simple. We'll talk about path. Path is nothing but, you may think this is Montgomery, this is Atlanta, and there is a path between Montgomery to Atlanta. It can be direct edge, or it can be via, like this is Atlanta, this is, you may think, New York, then you may think this is Vegas. So there is a path from Montgomery via Atlanta, via New York to Vegas. So this is an example of a path. So path is sequence of edges that begins at a vertex of a graph. Here it is, it begins from Montgomery and travels from vertex to vertex along edges of the graph. That's the path. We all know what is path. You don't need any computer science background to say what is path. Path is not that is only directed edge, means Montgomery to Atlanta, there is a direct edge. But path would be, it will start from a point, then you will go through one vertex to vertex, and it will up to the destination. Suppose your destination is Vegas, your source is Montgomery, and there is a path. Now you may think Vegas to London. There is no land path, right? There is an ocean in between. So you may think there is no path from Montgomery to London. Don't think about air path. There is air path. Only think about the land path. So in that, if you think of this land, only land path, don't think about air path or ocean path. You cannot take ship or airlines, anything. So in that way, Montgomery to Vegas, there is a path, but no path from Montgomery to London. So this is one path. And here we'll also talk about very simple topic, that is connected and disconnected graph. So graph can be connected as well as disconnected. So in this example, if you think the whole thing as a graph, so you can think there is no path from Montgomery to London. So it's a disconnected graph. So there is no connection. So it's a disconnected graph. So we can take one example. So this is one graph. These dots are vertex. This is one graph. Suppose graph G. Another graph is so this whole thing is also a graph. Suppose this is called H. Now see, in G, there is a path between any pair of vertices. You may think this is one vertex, this is another vertex. See, choose any two vertices, there should be one path. So for these vertices, there is a path like this. There is many other paths. But so this is a connected example of a connected graph. And here you can see there is no path between this node and this node or this node. So this is disconnected graph. So this is connected and disconnected. So graph can be connected as well as disconnected graph. But majority of the time, whenever we talk about graph, we mostly focus on connected graph, mostly. And similar to connected, disconnected graph, there is another important point is connected components. Connected components is very simple. Means if you think of this graph H, graph H has two subgraphs. So this graph has two subgraphs. This is one subgraph may call H1. This is another subgraph H2. So connected components means this disconnected graph has two individual connected components or two individual connected subgraphs. So connected components is nothing but connected subgraphs. So in this graph H, you have H1 and H2, two connected subgraphs. Even if you think of this graph G, so let's draw it again. So this was your graph. Now, if you delete one vertex, suppose this vertex, this is one vertex. If you delete that vertex as well as incident edge on that vertex, then what will happen? Let's see. If you delete that vertex, then what will happen? Okay, deleting and all incident edge. Okay, I am deleting all incident edge. So I have deleted only one vertex along with all incident edge on that vertex in this graph G. And what we get this is one connected subgraph, this is another connected subgraph. So deleting that particular vertex make this graph G as disconnected graph with two connected components. So deleting that vertex makes the graph G as disconnected graph with two connected components. It is an important property. If that happens, then that vertex which we deleted, that vertex will be called cut vertex. Cut vertex. That means if you cut that vertex from that graph, it will make the graph disconnected. So that is the cut vertex. Similarly, you may think cut edges means if you delete a particular edge, if that deletion makes the graph disconnected, then it will be called cut edge. So let's take one example of cut vertices and cut edges. So this is one graph. A, B, C, D, E, F, G, H. So A, B, C, D, E, F, G, H are the vertices, and there are a couple of edges are there. Now let's find cut vertices as well as cut edges. So if you think of cut vertices, obviously if you delete C from this graph, and when you delete C means you also need to delete all incident edge on C. So you will delete this edge, this edge, this edge. So if you delete those edges along with C, then there will be two components. So this will be one component and this would be another component. So deleting C will make this graph disconnected. So obviously C is one cut vertex. Another one is B. If you delete B and all incident edge, then what will happen? It will look like this. This is BA and this would be D and C. If you think only this small part, then see this is one component this is another component, only vertex, no edge is there. So also if you delete B, then you will make the graph disconnected. So C and B both are cut vertices, because if you cut those vertices from the initial graph, then the graph will be disconnected. But if you think of G, if you delete G, nothing will happen. The graph will remain connected. Let's see if that is true. If you delete G, okay, I'm deleting G as well as the all incident edge of G. So if we delete all incident edge of G, okay, still it is connected, right? Similarly, you can delete, if you think of E, okay, E is also there. If you delete E, then the graph will also be disconnected. So not only CB, E would be also a card vertex. So if you delete E, you can see the graph will also be disconnected. And what would be the procedure of deletion or removal of a vertex? You will remove the vertex as well as all incident edge on that vertex. Okay, now think about the cut edges. Okay, let's draw the graph again. Otherwise, it becomes difficult. So A, B, C, D, E, G, H. So obviously, if you delete this edge, CE, if you delete this edge, then obviously the graph will be disconnected. So obviously CE is one edge. If you delete that edge, it makes the graph disconnected. So C is one cut edge. Another cut edge would be here AB, this one. If you delete AB, what will happen? A will be like this. A will be like this. You deleted AB, then it will look like this. So A here and B, C, D. So this is one component. This is another component. So it will also make the graph disconnected. So the cut edges would be A, B, and C. So these are two cut edges. So let me write cut vertices, which might be confused when we would cut one vertices or remove one cut vertices. So it would be removal of a vertex from a graph and all incident edges. So that is the procedure to remove a vertex, to find out cut vertices. So we have talked about cut vertices and cut edges. Okay, next we can, one homework would be, this would be one graph. A, B, C, D, E, F. And you need to find cut vertices and cut edges. And it may happen that there is no cut edge in a particular graph, or there is no cut vertices in a particular graph. It may be possible. It's not that every graph will have those cut vertices or cut edges. In this graph, you can see if you delete C and all incident edge on C, obviously the graph will be disconnected. So this would be your homework. You just look into that. And I don't think it has any cut edge. Just verify that. This graph most probably will not have any cut edge. Okay. So we have learned path. Path is nothing but like from A to E, there is a path via C and D or C and F. So there is a path there should be a path in a connected graph between every pair of vertices. Similar to path, there is also called circuit. So circuit is same as path. Only difference would be the starting point equals to ending point. So where you will start your journey from Montgomery, you go to Atlanta, then you go to New York, then you go to Vegas, then you go to maybe Utah, then you come back to Montgomery. So this is kind of cycle. So this is circuit. So circuit is also a path where the starting point or starting vertex is same as your end vertex. So that is circuit. Okay, now we'll take another one example of two graphs where we need to find out whether those two graphs are isomorphic or not based on whatever we have studied so far. So example. So this is graph G, this is graph H. Now let's see whether these two graphs are G and H isomorphic. So check number of vertices in both graphs, then number of edges in both graphs, then degree sequence in both graphs. So number of vertices would be 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 5, 6. Number of edges would be 1, 2, 3, 4, 5, 6, 7, 8, I think. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 3, 6, 8. Yeah. And degree sequence. If you see degree sequence here, it would be this. For this one, it would be 2. Then for this one, it would be 1, 2, 3. For this one, it would be 1, 2, 3. For this one, it would be 2. For this one, it would be 1, 2, 3. For this one, it would be 1, 2, 3. And here degree sequence would be, for this one, it would be 2. For this one, it would be 3. For this one, it would be 3. It is 2. And it is 3. Then it is 1, 2, 3. So see whether their degree sequence is same or not. There are 4 vertices with degree 3 in graph G. Here there are also 4 vertices with degree 3 in graph H. Also, there are 2 vertices with degree 2 in G, same here also. 2 vertices with degree 2. So all those 3 conditions which we studied to check whether the 2 graphs are isomorphic or not, all 3 conditions are being satisfied here. But there is isomorphic means they should be the same. So we need to check whether any other things that looks like they are different or not. So if you think here, we have one circuit. And what is the length of that circuit is 3, because only 3 vertices are there in that circuit. So in this graph G, H, here we have circuit with length 3. But here we also have circuit, but the length is 4. So here we have circuit with length 4. Hence, they are not isomorphic. So again, there is no straight cut rule that you can follow. You need to check everything. So first, those three conditions you need to check. And after that, you need to check whether there is a circuit with the same length or not. So we need to, throughout, we'll study again new rules. So we need to follow many those things. So it's impossible, it's very difficult to say whether two graphs are isomorphic, but it is easier to say whether two graphs are not isomorphic. Okay. I hope it helps, Aditya.
Yes, sir.
Okay. Let's I'll write one statement. You need to say whether it's true or false. First, I'm sorry that I cannot give you too much time because I need to finish a decent amount of the syllabus. Because we have only less than 1 month in our hand. So I want to want to complete a decent amount of syllabus so that after completing this course, you should know some basic things. It is expected when you take data structure or algorithm, those courses, you should have some background before taking those courses. I'm trying to do that. That's why I'm not giving you too much time for practice. But strongly, I'd suggest you, when you revisit this lecture, pause the lecture and solve each example by yourself first. Then go for the solution. And I am using one textbook. Actually, that textbook is very famous textbook, Discrete Math by Kenneth Rosen. The writer name is Rosen. Kenneth Rosen, Discrete Math. It's McGraw publication. It's a very famous book. When I was a student, I also followed this textbook. Even if you follow the textbook, you don't need me. It's very classic textbook, I would say. So if it is at all possible, you can purchase this textbook. It's a classic textbook. Even if you, I think you can get soft copy of that textbook in the internet. Maybe. Okay, so let's discuss the, okay, I am writing one statement. Now your job is to check whether that's a true statement or false statement. The statement is, there is a simple path between every pair of distinct vertices of a connected undirected graph. So it is given that you have connected undirected graph, and the statement is saying that between every pair of distinct vertices, there is a simple path. Simple path means no repetition of edges. So no repetition of edges. So you will consider one edge only once, not repeat. No, you cannot repeat one edge. So there is a simple path between every pair of distinct vertices of a connected undirected graph. So let's assume this is your connected undirected graph. Make it complicated. Okay. So this is one connected undirected graph. And choose any two vertices. Suppose this is one vertices I and this is another vertices j. So it is saying that there is a simple path between every pair of distinct vertices. So I and j are distinct vertices. There is a simple path like this. Also, there is a simple path like this. So since this is connected, obviously the graph has to be connected. If it is connected, then obviously there is a simple path between every pair of distinct vertices. So the statement is true. And this is an important observation, because we will study different algorithms. You will study different algorithms in your algorithm course or data structure course based on this assumption. This is not assumption, this is a true fact. If a graph is connected, then obviously there should be a simple path between any pair of vertices. Okay, so we have studied cart, vertex, cart edges. Related to cart vertex, we can also have that is called vertex connectivity. It is very similar to cart vertex, means number of vertex connectivity is nothing but minimum number of vertices required to make a graph disconnected. So that's the vertex connectivity. So it is minimum. First of all, this is a short form of minimum. Like this is a short form of writing between. You might be confused. So the minimum number of vertices to be removed to make the graph disconnected. That is your vertex connectivity. So let's take one example. We already took one example. Like in the previous example here we used, this one. So here, so C, B, or E, all are cart vertices. So if you delete only one, either one from C, B, E, any one, then the graph will be disconnected. So for this graph, the vertex connectivity is 1. Similarly, this one, if you delete only one vertex like C, then the graph will be disconnected. So vertex connectivity is 1. But if you think of another vertex, suppose this one, let's draw it. A, B, C, D, E, F, G. So this is a graph. Is there any cart vertices? First of all, is there any cart vertices? That means after removing one vertex, the graph should be disconnected. So if you remove vertex G and all disconnected, all incident edges, then still the graph is connected. Because if you delete G, see, just assume you are deleting G. Let's delete G. If you delete G, it's still connected. Similarly, you can verify this graph doesn't have any cart vertex. Means there is no such vertex exist in this particular graph after removing that vertex, which will make the graph disconnected. So no cart vertices. But if you think, if you delete B and G both vertices, B and G both vertices and all incident edge on B and G, then the graph will become disconnected. Let's see. So you will remove B and G both. So you will have A in one side and this part will be in another side. So this graph will become disconnected if you remove B and G together. So if you remove B and G together, then the graph will be disconnected. So vertex connectivity for this graph is 2. That is, you need to minimum number of vertices that you need to delete to make the graph disconnected is 2 for this graph. Hence, the vertex connectivity is 2. Similarly, you can also think about the edge connectivity. The concept would be the same. That is the minimum number of edges that you need to delete to make a graph disconnected. So let's draw the graph again. If you draw the graph again, it was the graph A, B, C, D, E, F, G. Then if you if you can check, if you delete either BG or CF, then this graph will become disconnected. If you delete CF or BG, so at the same time, if you delete, if you delete two edges at the same time, like BC and GF, yes, if you delete edge BC and GF at the same time, so let's delete. So you are deleting BC and GF. So it will make the graph disconnected. So the edge connectivity of this graph is also 2. So this way, and if you think of this graph, yeah, for this graph, the edge connectivity would be 1, because if you delete this particular edge, this graph will it will become disconnected. So edge connectivity for this graph is only 1. So this is edge connectivity and vertex connectivity. And edge connectivity is nothing but minimum number of edges that you need to delete to make the graph disconnected. Okay. Okay. Now we'll talk about two important graphs, very popular, those graphs. One would be, is called Euler circuit and Euler path. Okay, before going into these details, is there any questions?
No, sir.
Okay. So Euler circuit and Euler path. So actually, Euler was a Russian scientist, and he was at that time 70s something, around 1750 or something, around 70s. So the background of Euler circuit and Euler path is based on, in Russia there is a island, and if I can show you, let me check whether if I can show you the diagram. That's very interesting to know. And this problem is actually coming from a real problem. Then that real problem will be represented like a graph problem, and then Euler proposed a solution of that graph problem. Okay, let me check whether I can use. Okay. Yes. Oh, where it goes, I don't know. Aditya, can you see this diagram?
Yes, sir.
Okay, then okay, let's discuss this way. Okay, this is one island. A, B, C, D, all are islands, and there is a river flowing around that island, and there are some bridges. That green one are bridges. So the problem, it is called the 7 bridges of Königsberg. It is in Russia. So the problem is people in this 70s, around 1736, 1736, Euler proposed this solution. So the problem is you need to traverse all bridges exactly once, and wherever you will start, you will end your journey at that point, and you need to cross all bridges exactly once. Is it possible or not? So that was the problem. So that the same real problem can be converted to this graph problem. This is same actually corresponding graph problem. So we'll talk about that, or what Euler proposed a solution. We'll talk about that. Okay. So that is the background. Yeah, and this is the text that I am using. I don't know whether you can see it or not. Discrete math. So the problem is, what is Euler circuit? The Euler circuit is a simple circuit containing every edge of the graph. So Euler circuit is a simple circuit. First of all, what is circuit? Circuit means your starting point and your ending point would be the same, and it would be a path which cover all vertices. So you will find a circuit and it should be simple. Simple means, okay, let me write what is circuit. Circuit is start and end nodes or vertices, both are same. Vertices are the same. This is circuit. And what is simple? Simple means no repeated edges. So there should not be any repetition of edges. So you need to find a simple circuit which contains every edge of the graph. In that example, edge means that bridge. So you need to traverse all bridges exactly once, and you need to come back to your starting point. So that is Euler circuit. And Euler path is same. Instead of circuit, you need to find a simple path. So Euler path is a simple path containing every edge of the graph. That is Euler path. So it's a path, not circuit. That means your starting point may not be the same as your end point. So it's not that you have to, while you have started your journey, you have to end your journey at that point. No. So that's the difference between circuit and path. So let's take example to understand these two concepts. Okay, this is one graph. Now, let's see whether Euler circuit is present or not. Euler circuit means your starting point. Let's assume this is your starting point. And you need to cover all edges exactly once, and you need to come back to your starting point. So let's start your journey. Okay, then here, then here, then here, then here, then here. So there is this Euler circuit in this graph. So because you have found one simple circuit covering all edges exactly once. So yes, there is a Euler circuit is present. So Euler circuit is present. And if there is Euler circuit, so obviously there will be a Euler path. Now take another example. Okay, this is one graph. You need to find whether there is any Euler circuit and Euler path. So let's see whether you can get any Euler circuit. Euler circuit means you will start from a point, you need to end your journey at that same point. At the same time, you need to traverse all edges. All edges should be crossed. So let's start your journey. Okay, all these edges, these edges, these edges, these edges, these edges. Okay, I can traverse all edges, but I started my journey at point A, but I end my journey at point B. That means there is no circuit, there is no simple circuit which cover all edges exactly once. So in this graph, no Euler circuit. But is there any Euler path? Yes. See this red line. Here we started our journey at A, then we reach C, then D, then E, then B, B to D, D to A, and A to B. So there is a path, simple path, which covers all edges exactly once. So in this graph, there is no Euler circuit, but there is a Euler path exists. Okay, let's take another example. So you need to find whether there exists any Euler circuit or Euler path in this graph. Most probably no, you need to do it by yourself. Another one would be like this. In this graph, this is another graph. In this graph, you need to find, is there any Euler circuit or Euler path? In this graph, I think there would be. Here you start, okay, then you go this way, then you go this way, then you go this way. So every edge is traversed exactly once, not more than once. So we have found a simple circuit which covers all edges. So yes, in this example. But here you will see no, you can't find any such Euler circuit or Euler path. Okay. So here one important theorem regarding the existence of Euler circuit. So the theorem is saying that there exists an Euler circuit in a connected graph if and only if each of its vertices has even degree. It is an important theorem. So it's saying that in a graph, there will be an Euler circuit if and only if each of its vertices has even degree. So choose any vertex. If the vertex has even degree, then there will be an Euler circuit. So let's see. This is one graph where we have found Euler circuit. Choose any vertex. C, it has degree 4, which is even. D, it has degree 2, even. Degree of E is 2, even. Degree of F is also even. Degree of G is also even. And we also find that circuit. Now see this one. Here we could not find Euler circuit. Instead, we found Euler path. So see, the degree of A is 3, which is not even, odd. Degree of D is 1, 2, 3, 4. This is even. Degree of B is odd, 3. So see, so it validates here. And also in this graph, choose any vertex E. The degree of E is 4. So which is even. Degree of D, C, B, A, all are even. The degree is 2 for those. And here you will see for this vertex A, the degree is 3. Vertex B, degree is 3. Vertex C, degree is 3. Vertex D, degree is 3. So there should not be any Euler circuit. So it is an important theorem. So it is saying that there exists an Euler circuit in a connected graph if and only if each of its vertices has even degree. This is one important property. If the graph, if every vertices has even degree, then there will be an Euler circuit. Why? What is the logic behind that? It's not difficult. First of all, you need to find a circuit. Circuit means if you start from Montgomery, just think you went to Montgomery to Atlanta, Atlanta to New York, New York to maybe Vegas, Vegas to maybe Utah, then Utah to, you come back to Montgomery. So choose any vertex. Choose any vertex. Suppose A. Choose any vertex. If you choose any vertex, see there is one edge incident to that vertex and another edge is towards the outside direction. Means in one path you will reach Atlanta, in a different path you will go outside Atlanta, because you cannot traverse one edge more than once. You need to traverse one edge exactly once, and it should be circuit. So for any vertex, you will see one incident edge, one outside edge. Means this edge, you will reach that point, and this edge, you will go outside that area or that point. So the degree, this one, this arrow will add degree to 1 to this vertex. This arrow also add degree 1 to this vertex. That's why it should be even. Whenever there is a path to reach a vertex, there should be another path to go outside of that area. So this is one path which leads to Utah. There will be another path that you need to take to move outside Utah. So there should be always even. One path to reach that destination, another path to go outside that destination. That's why this has to be even always, to find a Euler circuit. That is the logic. So this is an important theorem to find whether there exists Euler circuit in a graph, in a connected graph. Another theorem to find the existence of Euler path instead of Euler circuit. Let's assume in this graph, suppose there was no Euler circuit, but there is a Euler path. So when we can expect there will be an Euler path. So another theorem, theorem 2, would be there exists Euler path but not Euler circuit if and only if it has exactly two vertices okay somehow it disconnected. Yes. So the second theorem, where there exists Euler path but not Euler circuit, if and only if it has exactly two vertices of odd degrees. So it will have exactly two vertices of odd degree, and all other vertices would be of even degree. What is the difference between theorem 1 and 2? Theorem 1 is saying that all vertices will have even degree. And theorem 2 is saying that there exists a Euler path but not Euler circuit if and only if exactly two vertices of odd degree, and rest would be even degree. So see this example. This one, we have found that no Euler circuit was there, but there was Euler path. See, this vertex has A vertex has degree 3, vertex B also have degree 3, D has degree 4, this one has degree 2, this one has degree 2. See, only two vertices are there with degree 3, that is odd. So it can be validated this way. So there exists Euler path but not Euler circuit if and only if it has exactly two vertices of odd degree. So these two theorems are very important. So let's take a couple of examples to grasp this concept. So this is one graph. CT. This is one graph. Now, is there any Euler circuit? Euler circuit means all edges should be of even degree. So the degree of D is 3. Degree of 3 is 3. Degree of C is 2. Degree of C is 2. Degree of B is 3. Degree of A is 2. So it follows the theorem 2. That means there is exactly two vertices of odd degree. That means in this graph, there is Euler path, but no Euler circuit. And let's take another one. So the degree of B is 3, degree of C is 1, 2, 3, 4, degree of D is 3, this one is 2, this one 1, 2, 3, 4, this one 1, 2, 3, 4, this one 1, 2. So there is exactly two vertices of odd degree. So you will find Euler path here, but no Euler circuit. You can verify that also. And another one would be another example. Okay. Here, if you check the degree, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and this one 1, 2, 3, 4, 5, 6. So there are 6 vertices of degree odd with degree odd. So there will be no here. There will be no Euler, neither Euler path nor Euler circuit. So no Euler path, no Euler circuit can be found here. So this is about Euler circuit as well as Euler path. And in your assignment as well as in your final exam, you can be sure that you will get questions from here and based on these two theorems that we have studied. And very similar to what we have studied, Euler path and Euler circuit. What is Euler path? Euler path and Euler circuit, we need to traverse all edges exactly once. So can we apply the same concept for vertices instead of edges? Means our goal is to cover or traverse every vertex of that graph exactly once. So in Euler path or Euler circuit, we covers every edges. Now we'll think about covering every vertex of that graph. So you need to find a simple circuit which cover all vertices of that graph, or you need to find a simple path which covers all vertices of that graph exactly once. And then it would be called Hamiltonian circuit and Hamiltonian path. Means when you have when there is a simple circuit, then it would be called Hamiltonian circuit. When there is a simple path, then it would be called Hamiltonian path. So a simple path in a graph G that passes through every vertex exactly once is called a Hamiltonian path. So this is a simple path which covers every vertex exactly once. In Euler path, it was every edge exactly once. Here, every vertex. And similarly, a simple circuit in a graph G that passes through every vertex exactly once is called a Hamiltonian cycle. So you need to find a simple circuit which will cover every vertex exactly once. And it has a large application, Hamiltonian circuit. And just let's take one example. Let's take example of Aditya. Suppose Aditya's mother asked him to visit Walmart, Kroger, Publix, CVS, and many other such destinations. This is Aditya's goal. Now, Aditya needs to find a shortest path to cover all vertices exactly once, to all destinations. So Aditya needs to visit Walmart, Aditya needs to visit Kroger, Aditya needs to visit Publix, CVS, but in any order. But he will visit one destination exactly once. That is called traveling salesman problem. Traveling salesman problem, very famous problem. And there is no efficient solution for this problem. Efficient solution means efficient in terms of time efficient. So TSP is a very famous problem, very famous. And it is one of the hardest problem in computer science. And if you can give an efficient solution for TSP, then you will get something like Nobel Prize. So you don't need to do anything in your rest of the life. So you need to provide an efficient solution. So this is one application here. So you will, when you will take a data structure as well as mostly algorithm course, then you will come to know more such algorithms, very interesting problems. So that is Hamiltonian cycle and Hamiltonian path. So let's take a couple of examples that will help us to grasp the concept of Hamiltonian circuit. This is one graph. This is another one. This is another graph. So suppose this is graph G, this is H, this is I. Now you need to find whether there is a Hamiltonian circuit. If there is no Hamiltonian circuit, then check whether there exists any Hamiltonian path. And in some cases, maybe there is no Hamiltonian circuit, no Hamiltonian path. So for this graph G, you will see, so what is Hamiltonian circuit? You need to find a simple circuit that covers all vertices exactly once. So for this graph, you may think, okay, I start my journey from here, then here, then here, then here, then here. Okay, so this is a simple circuit, and it passes through all vertices exactly once. And my starting point and ending point is same. So here, yes, we found both Hamiltonian circuit as well as Hamiltonian path. And again, the difference between Hamiltonian circuit and Euler circuit is here you need to pass all vertices, not edges. But in Euler path or Euler circuit, you need to pass all edges. Let's talk about H. Here, whether you can pass all vertices exactly once. Okay, I started from D, then C to B, then B to A. Okay, here I have got one simple path, but not circuit, because my starting point is D, but my ending point is A. So it's a simple path which covers all vertices. So there is a Hamiltonian path, but not circuit here. So no circuit. And here, if you check, neither Hamiltonian path nor Hamiltonian circuit exist, which cover all vertices exactly once. Because if you see of this one, the path which leads to this vertex, there is no path outside this vertex. So you have to use this edge again. So there will be no Hamiltonian circuit or no Hamiltonian path for this graph. No circuit, no path. Okay. Okay. Another difference between Euler circuit and Euler path is, in case of Euler circuit, we have seen two very simple theorems, theorem 1 and theorem 2, to find out whether there exists any Euler circuit or Euler path in a graph. Very easily you can find this thing in very efficiently, that whether all vertices has even degree or all vertices except exactly two have even degree. So you can verify that very easily. But how to check whether there exists a Hamiltonian cycle is there is no easy or no efficient solution exists till today. That's why I said this traveling salesman problem is very hard, one of the hardest problem. So there is no efficient solution to say that whether there is a graph, there exists any Hamiltonian circuit or Hamiltonian path in a graph or not. No efficient solution like Euler circuit or Euler path. But there are two theorems which will give you not exact condition, but sufficient condition to verify whether there exists any Hamiltonian path or Hamiltonian circuit. But it doesn't mean that one graph doesn't satisfy those conditions. That doesn't mean that there will be no Hamiltonian circuit. It may happen that some graphs do not satisfy those conditions, but still it is there exists Hamiltonian circuit. So that's not, those conditions are not sufficient enough to say that whether there exists any Hamiltonian circuit or Hamiltonian path. So let's talk about those theorems. One is Dirac's theorem. Dirac's theorem is saying that if G is a simple graph with n vertices where n is greater or equals to 3, such that the degree of every vertex in G is at least n by 2, then G has a Hamiltonian. That means it is saying that degree of every vertex in that graph should be greater or equals to n by 2, where n is the number of vertices. So let's take one example. This is one example. Here n is 4. And what is the degree of every vertices? Degree of this vertex is 2, this one 2, this one 2, this one 2. So it satisfies this one. Now again, I said that it doesn't matter that if there will be some graph which will not satisfy this condition, because it's not a necessary condition. So that graph doesn't satisfy this condition, but still there will be some Hamiltonian cycle. Let's take one example. Okay, this is C6 graph, cycle graph with 6 vertices, 1, 2, 3, 4, 5, 6. Now see, what is n here? N is 6. And what is the degree of every vertex? Is 2, 2, 2, 2, 2, 2. And according to here, the degree should be 3, according to this formula. But it is actually 2. So it doesn't satisfy that condition, but still you can find a Hamiltonian cycle like this one. Very easy Hamiltonian cycle. So this is not a necessary condition. But if one graph satisfies this Dirac's theorem, then there will be one Hamiltonian circuit. So similar to this Dirac's theorem, very easily we can get another theorem, which is called Rosen's theorem. We can derive this Rosen's theorem from Dirac's theorem directly. That is saying that if in degree of U plus degree of V, U and V are two distinct vertices. Any two vertices, degree of U and V should be greater or equals to n, where for every pair of non-adjacent U and V. Means U and V are not adjacent. Means there is no direct edge between U and V. So U and V is such vertices, non-adjacent vertices, then degree of U plus degree of V should be greater or equals to n. So what is Dirac's theorem is saying? Degree of each vertex should be greater or equals to n by 2. So if degree of U, according to this Dirac's theorem, degree of U should be greater or equals to n by 2. So let's assume it is n by 2, the minimum value, plus degree of V would be also n by 2. So n by 2 is actually n. So this theorem, Rosen's theorem, is actually coming from Dirac's theorem. So every vertex will have, it is saying that every vertex will have degree of at least n by 2. So both are saying actually almost same thing. So Dirac's theorem, if Dirac's theorem holds, which implies that Rosen's theorem also holds, but not vice versa. The opposite might not be true always. So if Dirac's theorem is satisfying, so obviously Ore's theorem will also satisfy. But the opposite is not necessarily be true. So they provide sufficient condition. So both Dirac's and Ore's theorem provides sufficient conditions for a connected graph to have a Hamiltonian circuit. But however, they do not provide necessary conditions for the existence of a Hamiltonian circuit. So they provide sufficient condition, but not necessary condition. Means if some graph satisfies this condition, so there will be some Hamiltonian circuit. But if there one graph doesn't satisfy this condition, that doesn't mean that there will be no Hamiltonian circuit. So it's a sufficient condition, but not necessary conditions. And again, no polynomial time algorithm exists to solve this problem. And it is called almost one of the hardest problem. Although it looks like very simple, but it is actually hardest problem to find, to come up with an efficient algorithm to solve this problem without manual intervention. And one application of Hamiltonian circuit is that traveling salesman problem. It is like this one, traveling salesman problem. There is one salesman who needs to visit each town exactly once. So he started from this town. He needs to visit each town exactly once, and there is no fixed order. He can visit one town in any order. And this should be connected graph, means there will be there will be an edge between every pair of vertices. So there is a connected graph. So there is a path between any pair of towns, two towns. Any pair of two towns, there is a path. So now the job of the salesman is to visit each town exactly once and return back to his hometown. And he can visit any town in any order. That is traveling salesman problem. Although it seems like very easy problem, but there is no efficient solution till today for this problem. So it is called one of the hardest problem, traveling salesman problem. Okay, is there any questions so far?
No, sir.
Okay, I know it's almost 2 hours, but I want to briefly continue our discussion so that I can complete the graph part by today. I'll not take too much time. I'm almost close to end, almost at the end. So another important graph is called planar graph. So planar graph is a graph is planar if it can be drawn in the plane without any edge crossing. What does that mean? So this is one graph, complete graph. Again, what is complete graph? Complete graph means there will be an edge between any pair of vertices. So this is one complete graph denoted by K4. K stands for complete graph and 4 means there are 4 vertices. So this graph is denoted as K4. So here it seems that, okay, named it A, B, C, D. It seems that AC, edge AC and BD are crossing one each other. But if you draw this the same graph like this way, CD, BD. So I'm drawing the same graph here. It's there is no edge crossing. So this K4 is a planar graph. So what is planar graph? A graph is planar if it can be drawn in the plane without any edge crossing. So no edge will cross another edge. So one application would be electrical circuit design. Another one would be road network. So suppose government wants to come up with the road network, and they will try to avoid edge crossing, because edge crossing will create problem like traffic, as well as signal problem, as well as high chance of accident. So they will try to avoid that edge crossing, that two roads will cross each other. So this is planar graph. And so planar graph means no edge crossing. There will be no edge crossing. So K4 is a planar graph. In your exam, you might have a question that is K4 a planar graph? Your answer would be yes. So this is a planar graph. So another question can be, is K3, 3 is planar? So what is K3, 3? K3, 3 is a complete bipartite graph. So it is a complete bipartite graph with 3 vertices, 3 edges. So generally it looks like this way. At the beginning of the today's lecture, we talked about bipartite graph. So complete bipartite graph means like this. There will be edge between every pair of vertices from this set to this set. So this is complete bipartite graph with 3 vertices, 3 edges. Three vertices in one set. In this set, there are 3 vertices, and in this set, there are 3 vertices. So that's why K3, 3. So total number of vertices would be 3 plus 3, that is 6. So the question is K3, 3 is planar? So let's see whether we can draw it without any edge crossing. So let's draw it. Okay, there is no edge crossing so far. Okay. Now this one is done. This one is done. Okay. Draw this one. Draw this one. So it is also done. Then draw this one and draw this one. Oh, this one is already done, so there is no need. Okay, so only see this one and this one. We cannot draw an edge between these 2 vertices without any edge crossing. So far there is no edge crossing, but now we cannot have any edge between these two vertices without any edge crossing. So the answer would be no. So K33 is not a planar graph. Okay. So here we'll introduce with one concept of called region. So this is one planar graph that we drawn before. This one, the complete graph that we drawn, this one. So what is region? Region in this graph, in this planar graph, we will have one region. This is region 1, non-overlapping region. So this is region 1, this is region 2, and this is region 3. And this is unbounded region, that is region 4. So in this graph, there are 4 regions. So a planar representation of a graph splits the plane into regions, including an unbounded region. That is here, that is R4. So R4 is the unbounded region, and R1, R2, R3 are bounded region, bounded by vertices. So I'm bounded by edges. So this is region. Now let's take another example. This is one planar graph. Planar because there is no edge crossing. So what are the regions are there? One region is this one, R2, R3, R4, R5, and unbounded region R6. So these are regions. And here we'll have one theorem, Euler's theorem. On Euler's formula, let's write it, formula for planar graph. And it is saying that G is a connected planar graph. Simple. All graph that we are talking about is simple, means no multiple edges would be there, no self loop would be there. So all are simple graph. So connected simple planar graph, and E is the number of edges in that graph, and V is the number of vertices in that graph, and R is the number of regions in that graph. So Eulers provide a formula to come up with a relation between number of edges, number of vertices, and number of regions. So the formula is R equals to E minus V plus 2. So this is the formula. The relation between number of regions based on number of edges and number of vertices. Let's take example of this one. So this one graph that we talked. So here number of regions was 4. One region, 2, 3, and this one unbounded. And what was V? V was 1, 2, 3, 4. What is E here? Number of edges, 1, 2, 3, 4, 5, 6. So see, what is 6 minus 4 plus 2, that is 4. See, we have 4 regions. Similarly, you can verify for this example, it holds true. So this is the relation between number of regions of a planar graph containing E number of edges, V number of vertices. This is important. So one question based on this, suppose a connected simple planar graph has 20 vertices, each of degree 3. Then what is R? R means number of regions. So number of vertices V is given, that is 20, each of degree 3. So last class we have talked about handshaking theorem. So the relation between E and V would be summation of degree of all vertices would be 2 multiplied by number of edges. So here degree summation of all degree of all vertices would be 20 multiplied by 3, that is 60, equals to 2E. Also, so E equals to 30. So this is the handshaking theorem that we studied last day. So from there we calculated number of edges. So if we, so easily we can apply the equation right now. R equals to E minus V plus 2. So E is 30, V is 20 plus 2, that is 12. So the answer would be 12. So this is about planar graph and the relation between number of regions based on number of edges and number of vertices. Okay, now we'll the last part of this lecture would be the thing that we talked about in the beginning, that is graph coloring. Graph coloring, that is assignment of a color to each vertex of the graph so that no two adjacent vertices are assigned the same color. That is graph coloring problem. And the number of minimum color is called chromatic number. So chromatic number is the minimum number of color needed to color a graph. That is chromatic number. So when we discuss bipartite, we need minimum 2 colors. So chromatic number of any bipartite graph is 2. And it is denoted as x of g. It is called Greek psi. So chromatic number of a graph, that is the least number of colors for a coloring of a graph. That is chromatic number. So the chromatic number for any bipartite graph would be chromatic number of any bipartite graph equals to 2. Okay, there is an important theorem. Again, this graph coloring problem is also an open problem. No efficient solution is known today. That to find for any graph, not only bipartite graph, for any kind of graph, what is the chromatic number? So it's an open problem. There is no efficient solution. Open problem means there is no efficient solution. Efficient means time efficient solution. So one theorem is four-color theorem. So it is saying that the chromatic number of a planar graph is no greater than 4. So it is saying the chromatic number of a planar graph is no greater than 4. So it is not saying exactly what is the chromatic number. It is saying that for any planar graph, only for planar graph, for any planar graph, the chromatic number should not be more than 4. It can be 4, it can be 3, it can be 2. So this is called four-color theorem. So let's take one example. So this is one graph, and it's a planar graph because no edge is crossed any other edge. So this is a planar graph. Now, how many colors does it need? So when you color one vertex, you need to make sure that no two adjacent vertices should have the same color. So you need to make sure that. So let's make it red. If I make it red, then I cannot make the adjacent nodes as red. So if it is red, then I can make it red because they are not adjacent. There is another vertex here. So no, it's not adjacent. So we can make it red. So yeah, that's all. We can use green. Okay, let's make it green. Let's make it green. Okay, we cannot make others green. Let's use yellow. So we can make it yellow. We can make it yellow because they are not adjacent. We can make it yellow. So for this graph, chromatic number is 3, because we can use only 3 colors, minimum 3 colors to color the graph. So chromatic number is 3. So we can see another graph. Okay, this is another graph. Here, if you apply color, okay, let's make it red. If it is red, then we can make this one also red. And anything else that you can make red? No, that's all. Okay, then use green. We can use this one green. If it is green, we can make it also green. Anything else that we can make green? No. Then let's use yellow. Okay, use yellow, this one, yellow, this one. Anything else? No. So we need another color. So let's use something like this one. If we apply this one, it is another fourth color. So the chromatic number is 4 in this graph. So, and both are planar graph. So you see the chromatic number or minimum number of color that is needed for a planar graph should not be more than 4. It can be 4 or less than 4. Okay, another question would be, which would be very important for your final exam. What is the chromatic number of Kn? So what is the chromatic number of Kn? What is Kn? I have already told you. Oh, what happened? Yeah. Kn is complete graph with n vertices. What is complete graph? Complete graph means there should be an edge between any pair of vertices. Edge between every pair of vertices. Last we talked about complete graph. So there should be an edge between every pair of vertices. So every vertex is the neighbor of every other vertices, because there is an edge between every pair of vertices. So let's take one example of, suppose this is K3 complete graph. This is K4. This is K5. So see, there is an edge between every pair of vertices. Now, if you use color, so if you make it red, no other vertices can be red. So you can make it blue, you can make it green, you can make it yellow. So how many colors needed? 4 for this one. For this one, it would be 3. See? Because every vertex is a neighbor of every other vertices. So the answer would be n. So you need n colors, because complete graph means there is a path between every pair, there is an edge between every pair of vertices. So for K5, it would be 5. So the answer, what is the chromatic number of Kn complete graph? That is n. N number of colors you need. And what is the chromatic number of bipartite graph? It is 2. Only 2 colors you need. And again, there is no efficient solution for finding this graph, the minimum number of colors for any kind of graph, that is the chromatic number. There is no efficient solution still exists still today. So these are all open problems. And if you can find a solution, you will get something similar to Nobel Prize. So it's very exciting to know these problems. And when we study this kind of problem, when you will study algorithm, you will come to know that many problems are related to each other. In high level, you might think that these two problems are totally different from each other. But when you study very closely, then you will see that one problem can be converted to a different problem. So if you can find a solution for this one hard problem, then that leads to the solution to all other hard solution of the hard problems. So it would be very exciting when you will study algorithm. And next semester, there is a high chance that I will teach data structure as well as your algorithm and maybe networking. There is a chance. but it's not finalized yet. Undergraduate networking, data structure, algorithm. That's all about today's topic. So we have mostly covered graph, and next day we'll use maybe maximum 40 minutes or something to discuss about tree. Tree is also a graph, or special kind of graph. So we'll briefly talk about tree, and then we'll talk about set, then relation, function, those things we'll cover. And by tomorrow, my plan is to release your assignment based on whatever topic that we have covered so far. In the meantime, if you have any questions or any doubts or any queries.
No, sir.
Okay, thank you for joining me today. And I understand it's more than 2 hours, and it's still Saturday. I appreciate your effort, and feel free to let me know if you have any queries, any questions. I'll be glad to help you. Tomorrow, as I mentioned, I'll release the assignment, and you will get only 7 days, so you don't have enough time. But it would not be just follow my lecture, it would be totally based on that lecture. And yeah, have a great Sunday. Okay, good, have a great weekend and take care. Bye.
Thank you, sir. Bye, sir.